All right, so this lecture will be recorded without using the camera. I'm going to try to do everything here on screen. So we've talked so far about how do we make sound. Okay, do you know how sound is actually created? You might remember that it has something to do with some vibration happening, some kind of periodic motion. So um, for example, the ringer bell that we had talked about, that bell is vibrating. That means that it's actually changing in its shape. It may be happening many times per second. The tuning forks were another example of something that's changing its shape rapidly, many times per second actually. If you remember, some of the markings on the tuning forks was 256 or 512, which corresponded to the number of oscillations per second that's measured in hertz. Today we're going to talk a little bit more about that. So we're going to relate two ideas, period and frequency, to each other. These are some of the most fundamental concepts of how we can discuss sound. The oscillator that we're talking about here is actually meaning any kind of thing that's oscillating. And let me give you some examples. For example, a violin, the body of the violin is actually vibrating quite a bit when the string is either plucked or there's a string, horse string kind of going across the string, so it's creating a vibration which is then coupling to the entire body of the violin, and then what you're hearing is that vibration of the body of the violin. Another example that we'll see in a moment is a gong. When you hit a gong, it's creating very complex vibrations, and in fact, we'll talk a little bit about that, and in terms of how we can classify different kinds of motion, some as being periodic and some as being maybe not exactly a periodic type of structure because of its randomness. Another thing is when you make a sound with your voice, you're creating your vocal cords, and you are moving both your tongue, and you're also controlling the rate of flow of air, and you're also changing something about the passage through your throat. So we'll talk some more about that later, but just to kind of get that idea that also there's vibration happening here. And if you put your hand onto your neck as you're talking, you'll actually feel that vibration, especially if you go to the lower frequencies, like you really feel something. So, all right, so continuing on, let's see, how do I go to the next slide here? Okay, so the objectives here, one is really important, is that we're trying to figure out how to convert between frequency and period. So just shortly said, frequency is the number of times per second an oscillation happens, and period is the amount of time that it takes for one oscillation to happen. The relationship between these is very simple. It's just frequency is equal to 1 over the period, or period is equal to 1 over the frequency. And we'll talk about that some more. We're going to create some graphs of position versus time for an oscillator, and we'll learn from that how to read off things such as the amplitude and the frequency, and then again relating frequency to period. We'll learn how to determine the amplitude, period, and frequency from a graph of oscillatory motion, and we'll investigate the factors that determine the period of a pendulum and a mass spring system. So one other thing to kind of keep in the back of your head is you might be wondering, does a pendulum or a spring and mass system relate to making music? Well, one thing that is kind of like a model for us in terms of thinking about periodic motion. In fact, we'll see that a pendulum and a lot of the spring motion that we'll be analyzing are oscillations that happen maybe, 2 or 3 times per second or 5 times per second. But in order for you to make actual sound that's audible, we'd have to have vibrations happening that are at least 20 times per second. So you can kind of keep that in mind, but we'll be looking at a few model systems to help us make some sense of what's going on. So a vibration that repeats itself at regular intervals creates a sensation of distinct pitch. So pitch is your psychological interpretation of what's going on. It's a sensation of how high or low a musical sound or note is. For those of you who are musicians, we might say something like a high or low register. But simply put, a high-pitched voice is, or a high-pitched sound, as you know, is woo, and a low-pitched sound might be woo. And the frequency is actually what we would measure with science. We would actually, for example, use some kind of measurement technique to count a number of oscillations that happen in a second, and we would report that as the frequency. So let's take a look at this little spring doodad that I have bobbing up and down on the right-hand side of the screen. We want to know, how does the mass actually affect the frequencies? So in other words, if it gets heavier, do you think that it would oscillate more slowly or more quickly? So you can kind of think about that for a moment. Well, you might have guessed that if the mass of this thing, that's the orange little block here, gets heavier, then the frequency at which it oscillates goes down. In other words, it oscillates less times per second. Think about that like in terms of, if you had like a car and you wanted to try and get it going, you wanted to push a car. The heavier it is, the more difficult it is to get going. So maybe it makes sense somehow that the heavier the mass, the lower the frequency. Conversely, if you make the mass very light, then the frequency that it resonates at can go much higher. So that's kind of a concept there. You'll see this in various iterations when we talk about different kinds of instruments. And we'll also come across a few counterintuitive little puzzles later on, especially as we begin to talk about resonance notes with regards to air, like for example wind instruments. So we'll discuss that more later. But anyway, the idea there is that I want you to get across this idea that the heavier the mass, the lower the frequency. I want you to kind of visualize that, and we have some demonstrations that will kind of help us to hone in on that. So how does mass then affect the period? Well, heavier mass is going to mean a longer period. That means the period means the amount of time that it takes to do one complete oscillation. If that's not obvious to you, that might be a term that you write down and make sure that you have on your crib sheet. That period means the amount of time that it takes to complete one full oscillation. So 1, 2, 3, 4. I'm counting the number of oscillations. I could also count from the top. 1, 2, 3, 4. You can see that that's the number of oscillations, or sorry, the number of full cycles that I see. And the timing between them, the amount of time it takes for me to say go between the number 1 and the number 2, that's a period. So a period might be as long as da, right? During that whole time that I held that tone, I was kind of showing the amount of time that it takes to complete one full cycle. Okay. Similarly, the heavier the mass. So as the heavier the mass, the longer the period. The lighter the mass, the shorter the period, meaning that it can oscillate up and down in a smaller amount of time. Good. So vibration is generally is thought of as something that repeats itself at regular intervals and creates a sensation of distinct pitch. Here's an example of a vibration without distinct pitch. That is a fairly complex sound. That is a gong, and you might notice that if you tried to hum what that was, it's not really a good way to hum it because it sounds like it's a lot of frequencies kind of all together. And so that inherent randomness actually means that this gong is not vibrating at any particular frequency. And so there's no distinct pitch involved. In fact, there's many frequencies involved. And so for our ears, we don't hear it as having any distinct pitch because it's not repeating itself at regular intervals. So simple harmonic motion, on the other hand, is when an object really is repeating itself at regular intervals. In other words, if I took a snapshot in time through one full cycle and I just replayed it over and over again, then I could give you the sensation that this thing is oscillating over and over. And in fact, for this animation, that's exactly what they did, is they just recorded one single animation of going through one cycle, and then they just put it on an auto repeat, on a loop over and over again. For those of you who like to surf around on the internet, you might find sometimes that there's little videos. The extension is .gif, or some people call it GIF or GIF, and that's what this is. And it's often just a short collection of images that are just made to be on repeat, and it can sometimes give you the illusion that it's a really, really long movie, but actually it's just repeating itself over and over again. So that's my idea of simple harmonic motion. Okay, so let's try an example here. Suppose I make the mass twice as heavy. What should happen to the period of the oscillation? Well, if you look in chapter 1 of our book, you see that there's an equation for period. And, well, it looks like a little bit of a complicated formula. It's got a 2 pi in there. Pi is the ratio of the circumference of a circle to the diameter of a circle. You might be wondering, why in the world is that in there? We'll get into that. But for right now, you can just take it as that's the formula. And the important part to pay attention to is what are the variables? Well, stiffness is one. And if you could just imagine for a moment a really stiff spring might be one that's like used as a car suspension spring. It's really hard to even move it just even a tiny bit. But if you give it a little pluck, it might go bang. But a spring with not very much stiffness at all, such as a slinky, you might be able to pull it very easily back and forth. So in other words, the restoring force that it has is not very strong. So also there's the mass on the bottom there. And this actually fits in really nicely with our picture that the heavier the mass, the shorter the period. And I wrote down this equation here at the bottom here that period goes like, that's the little tilde here. I ignored all the rest of those things. 1 over the square root of the mass. Okay. So I'm going to give you a moment. Please pause here and try to figure out what should happen to the period of the oscillation. Okay. Okay, and we're back. So the mass becoming twice as heavy, what should happen to the period of the oscillation? Well, here I can say that if I put, let's say that the mass was 1, okay, that's a nice thing. So then you can ignore the rest of these variables here, or you might imagine that I had chosen some mass such that with the rest of these variables, let's say that the period was 1 second. Okay, that's good. So let's say that this is our formula here, that the t, the period, is 1 over the square root of 1. Well, that would be 1 second. Now if I made the mass twice as heavy, I'd have 1 over the square root of 2. Well, you can plug that into a calculator, but you're going to find that the square root of 2 is approximately 1.4. And so if you plugged in a 2 instead of a 1, you might think, oh, well, maybe if I make the mass twice as heavy, then the period becomes half as much. But that's not actually true. Because of the square root, it's going to actually become, it'll be divided by 1.4. So I would answer D for this particular question here. And you can convince yourself by plugging in some realistic numbers and comparing them to each other. So just a little bit of taking a moment to plug in some numbers. So and you'll actually find. So for example, if you're not sure what to do, plug in the stiffness as 1 and calculate, and the mass as 1 kilogram, for example, and plug in that whole thing and figure out what your period is, and then write down that number, and then try it again, but now just plug in everything the same except for the mass is equal to 2, and you'll see exactly what I'm talking about. That those two scenarios, the second one is going to be divided by 1.4 or approximately multiplied by 0.7. So if you're getting that, you're now beginning to see mathematically how we can relate these quantities, period with mass. So for a periodic oscillation here, we generally have a way of graphing these things. And you're going to see that we're going to actually graph it in a variety of different ways. For example, we might be graphing the motion of an object at a particular place. We might say, oh, this violin is oscillating up and down by a few micrometers or millimeters or something like that. Or we might be plotting the pressure at a given point, what kind of pressure we're actually measuring. So here sometimes you see that we write the period as P. I think I would tend to use T here, capital T, instead, but you can see down here where we have this capital P. This is our period, or you could say capital T. This is the time that it takes to repeat the motion from the crest to the next crest. Or you can go from the trough to the next trough. That's also the same period. Or you can pick a midpoint and say going from one midpoint, not to the next midpoint, but one complete cycle. So you can see that that timing is the same. The time that it takes to go through one complete cycle is called the period, and that's going to be in units of seconds. The amplitude is going to be the midway point up to the peak, or if you want, the midway point down to the bottom. Both of those are the same if you take the absolute value. And this tells you how large a vibration is. Finally, we can look at the frequency, and we can just simply take the period and take 1 over the period to figure out how large a vibration is. In fact, let me just try something here. We'll do a couple of little calculations together here. So I'm still recording, and I'm going to make my font big. And for example, if I had a period equals to 0.5 seconds, my frequency would be equal to 1 over the period. So that would be 1 divided by 0.5 seconds, and I'm going to put that in parentheses just to make sure that it's super clear what's going on here. And 1 over 0.5, that's the same thing as 1 divided by 1/2 of a second. And if you want, then if you remember that if you take 1 over a fraction, that's like just flipping over the fraction to make its reciprocal. And you'll find that that's going to be 2 inverse seconds. So I could do like this, inverse seconds, oops, maybe like this, 2 inverse seconds. Or we also call this as a hertz. So 2 hertz, it means 2 oscillations per second. Another example is, let's say that the frequency is equal to, let's say 5 hertz, okay? So that means we have 5, so let's say this means 5 oscillations per second, okay? And if that's true, then what is the period? Well, we can see that the period then should be equal to 1 over the frequency. So that's going to be equal to 1 divided by 5. And this is inverse seconds, or 1 over seconds. Okay, so I could write this as 5 times seconds inverse, something like this. And that's going to be, we're going to flip everything, both the number, so we're going to get a 1/5, or 1 divided by 5 is 0.2. And then we're going to take 1 over inverse seconds, so basically 0.2 seconds, or 1/5 of a second will be our period. Okay, so that at least helps you to kind of see how that works. Maybe I'll write here that we often use T for period, but sometimes you'll see it written as P. So I'd like you to be flexible around that, but know that the period means the amount of time that it takes to complete a full oscillation. Okay, so we're going to continue on with the slides here. Now talking about simple periodic motion, you notice how it's like a perfect sinusoidal wave, right? It goes down, it goes up, it goes down, it goes up in a very smooth way. But there's other kinds of periodic motion too, and this is kind of a nice example, 3 different types of periodic motion here. You might notice that the top one and the bottom one, they kind of look like triangles a little bit, and we'll actually see that certain shapes of waveforms actually correspond to certain types of sounds, or sounds that you can sort of identify. The one in the middle actually looks a little bit more like little pulses or something like that. So each one will kind of have a characteristic sound. So the displacement means how much something is moving up and down by. For example, a speaker might be moving kind of up and then down and then up and then down. Or it might be moving up, down, and then flat, and then up, down, and then flat. And these oscillations may repeat themselves hundreds or thousands of times per second, and that's totally fine. That's a doable thing. And in fact, we do it every day. In fact, we're doing it right now because I'm talking. And what you'll learn very soon that talking happens in a frequency range that's somewhere in the hundreds of hertz range. So that means hundreds of times per second there is a vibration happening, and our ear is able to interpret that information as sound. So, okay, so this is complex periodic motion. And the most important thing that I want to drive home to you in this part here is that vibrations make sound. So in other words, a simple harmonic motion we call as a sinusoidal motion, or simple harmonic oscillations. I'll refer to all those things as being the same. Those all produce a sinusoidal waveform. I'm going to show you about vibrations making sound. We'll just watch the first part of this video here. If I can get it to load. Let's see if I can get this to load. Mm-hmm. Let's see here. We'll open that up.
I hear all the time people saying, I don't know if I can do Tai Chi because I'm not very coordinated. Or
Please ignore the ads. Okay.
Hello, Internet. How's it going there? This
So
is
these
a
guys,
slow-mo guys video.
these guys are going to put some paint onto a speaker. It might sound pretty weird. Why are they putting paint onto a speaker? So they're going to show you that when a speaker goes up and down, it is actually making some vibrations, and so they're going to visualize those vibrations. Here they've poured some paint onto the speaker.
Up all the way to... No, there's no 11.
Yep.
Get some predictive focus on the go.
Predictive focus.
So if I focus on the actual paint, it's going to immediately go out of focus, so I'm going to focus about here. So that as the droplets are at their apex...
Good word. Good word.
It's going to be a focus. Alright, ram it.
Yeah?
Yeah. That's good.
Yeah.
Alright, have a look at the playback. Okay, let's go. Oh, you can see the speaker start to move. Oh, wow. That is awesome. I like how the green is moving because it's the wateriest and the orange isn't moving yet.
Yeah.
That is awesome.
So it seems as though the more watery colours, they're the ones that bounce first.
Yeah, this time I've tried to mix them up so they're all kind of equally...
So you can see the speaker is moving up and down. And the really interesting thing here is that it's got all these different colors of paint. It gives a very nice visual about how sound is actually made, is that really it is moving up and down. You can see that it's pushing these little droplets of paint up and down as a way of visualizing that. So I really love the way that the colors swirl together. It's a very artistic creation that they've made there. So I put the link on there. You can watch all of it if you're interested. Please do. It's a kind of nice moment to reflect on the beauty of sound and the visualization of it by using this interesting technique. So, all right, we're back. We're going to head over to the slides again here. That's the paint on the speaker. Now, why did I show you that? It's because the speaker moves back and forth. And if you look at our first activity, which is this, what is it called, sound waves, then you see that there was a little bit talking about the physics of how a speaker is actually working. Certainly I don't expect you to be able to understand in depth, but I think I'd like you to know that there's a magnet involved that somehow by electricity is pushing the cone of the speaker back and forth, and that's what's making pressure waves. And so in a similar way that pressure waves are being made, you can also see that it can push paint up and down, that it really does have that, that force. But we had to watch it in slow motion because usually when a speaker is playing sound, it's oscillating up and down many hundreds of times per second. Okay, so here's some of our terms. You've got to know these. Frequency, period, amplitude, and what an oscillator is. Okay, so hopefully you already know something about each of these things, but we're going to continue to explore these to make sure that it's nice and clear. So to put into equation land here, the period is just 1 over the frequency. So it's the amount of time that it takes to complete one cycle of an oscillation. The frequency, on the other hand, is 1 over the period of an oscillator. And remember that an oscillator is just something that moves back and forth in a periodic fashion. It doesn't have to move necessarily sinusoidally, but it should move in a way that is periodic, meaning that it repeats itself in its motion. All right. So imagine for a moment that you were trying to describe to somebody the motion of a pendulum, and they maybe either lacked vision or that they just weren't in the same room. They weren't able to see it. How would you explain that to them? Can you imagine some ways that you could explain that? So maybe take a moment if you're watching this with someone and just see if you could describe a pendulum going back and forth. What would you say? What would you need to measure to describe the motion of this pendulum exactly? Well, what would be the parameters? Would you need to know, for example, the length of the string, for example, or maybe how much it has moved away from its equilibrium position, which would be this position that you can see here in the center. So an oscillator is a system that has motion that repeats in cycles. And so there's actually a lot of examples of this, but 3 here are a pendulum moving back and forth, a mass on a spring that's moving up and down, and also a vibrating rubber band. If I gave you a rubber band and you plucked it, it would actually move back and forth very rapidly. And you could even, if you made it a tighter rubber band, you could actually hear it vibrate at higher frequencies. And this would tell you that in fact it is a periodic motion, so it is a kind of oscillator. So so we will look in the activity about oscillator examples, and you could actually see this kind of motion. I think you actually have an idea already in your mind, but I think it's also good to experience that. And some other examples of different kinds of oscillations are musical instruments. As I mentioned, the body of a violin or of a cello is vibrating. Same thing with a drum. Geological formations, such in an earthquake, are also oscillating. Skyscrapers are actually meant to oscillate back and forth when they're in the wind. That actually, just like trees sway in the wind, it keeps them strong and keeps them from breaking. If they're too rigid, then they can actually break under the force of the wind. And another thing that's interesting is that atoms inside of a solid are actually also vibrating. In fact, since the atoms are closer to each other in a solid compared with in air, the sound can actually travel faster in solid materials, which is one of those things that you saw that through iron or steel, for example, the speed of sound is much faster than, for example, in air. Okay, so there's atoms themselves inside of a solid are actually vibrating. Okay, so if we watch a pendulum swing back and forth, we might ask, well, what is its cycle? We could say, well, it's the time that it takes to go, let's say, from all the way from the left side to the right and then back. And then once it's gotten back to the left side, we could call that one cycle. You don't necessarily have to call that as a cycle. It could be the other way. It could be from the right-hand side going to the left and then back. That could be one cycle. Or it could be somewhere in the middle, and that it goes middle to the right to the left and then back to the middle. The only problem with that one is that it's hard to know exactly when is the middle, because it's not stationary in the middle. It's always going the fastest when it's at the bottom. So in any case, what would be the goal of this full cycle thing is that we would want to figure out how long does each cycle take. The full cycle is the time that it takes to complete back and forth motion. The period is the time that it takes to complete one full cycle. So the cycle is basically just the thing that you're measuring, and the period is the amount of time that it takes to do that. We measure the period in seconds. What could you do to change the pendulum period or the frequency or so to make it make the period make the cycle happen in a faster, meaning shorter amount of time, or slower, meaning in a longer amount of time? What factors do you think that would determine its period? Do you think that changing its mass would affect that? What about the length? So just to flash back again, what are the definition of the period and the frequency? We can look at the period of different kinds of oscillations. So the Earth, in its rotation, that just means the length of one day, is 24 hours, or is about 86,000 seconds. Your heartbeat, what's the period of your heartbeat? Well, you might remember that it depends on if you're exercising or not. And if you're at rest or so, it should take about 1 second. And if you're exercising, maybe it takes a little bit less than a second, maybe even half a second for one full cycle. The minute hand on a clock, what is the period of that? Well, thinking about on a clock, the minute hand is going around the clock every hour. So I would say 1 hour is the amount of time that it takes to go around. A classroom pendulum. So if we set up a pendulum, maybe we have a length of a meter or so. We're thinking like a grandfather clock. It's ticking, talking back and forth. It's about a second or two, and we'll be exploring that more soon. So the frequency is how many cycles are completed in 1 second. The frequency is measured in hertz, and the 1 hertz means 1 cycle in 1 second. Good. So the frequency is how many cycles are completed in a second. What are the frequencies of these oscillators? Well, your heartbeat, if it's 1 second per cycle, that must also mean that it's about 1 cycle per second. If it's half a second, that means you're going to get 2 beats per second, right? So like 1/2 a second, another half a second. So now you did 2 in 1 second. A fan that rotates 360 times per minute, if you think about that, 360 times per minute, well, there's 60 seconds in a minute. So one thing that we could do here, if I wanted to do this out mathematically, let's actually get my my sort of notepad here. So for this one here, for frequency, 360 cycles, I'll just write cycles per minute, and I can multiply by 60 seconds. I'm sorry, I'll do 1 minute divided by 60 seconds. And in fact, well, here, I'll just take the time that it takes to make this be a kind of a good mathematical looking thing here. So I'll do this. Let's see if I can turn it into an equation. And I wanted to make it as kind of so you can really see it as a fraction. Let's do it like this. So let's do 360 cycles per minute. Okay, good. And I'd like to multiply that by, well, 60 seconds are in 1 minute. Remember, this is the old multiply by 1 trick. And if you notice here, this means that well, I didn't do it correctly because I need to. That is certainly true, but I need to put the 60 seconds on the bottom, 1 minute on the top. That's still also 1. And now you notice that the minute here can cancel out. So I can cross that out, and I can cross out this here as well. I'm now left with 360 cycles per 60 seconds, which is now going to be 360 divided by 60, which is just going to be 6. And this is going to be 6 cycles per second, which in other words means 6 hertz. So that's how we get that. Okay, just wanted to show the math very clearly. And finally, the vibration of a guitar string. If I can start again here. The vibration of a guitar string is usually somewhere in the range from 100 hertz up to 800 hertz. And I happen to have a guitar right here, so I'll just play one of the lower notes. And I'll go to the higher one. This is more oscillations per second. More oscillations. And finally, the one at the top is oscillating at, I believe, 2 times the frequency. No, 4 times the frequency, but we'll get there. So the higher the pitch, then the more oscillations per second are happening. And if we look actually at the guitar string, you can actually watch it vibrating back and forth. You can actually see that, and even if we look in slow motion, we can actually see that happening. Okay, so that's the vibration of a guitar string. There's an interactive equation, and I'll provide these electronic resources here. This one is very, very simple, but I think it's still worth just playing around with it so that you can get a sense for how this works. You can try out what is the frequency of an oscillator that has a period of 1 second, or 2 seconds, or 4 seconds, and I really want to make sure that you know how to calculate those kinds of things. Simply putting into your formula there 1 second for t, you'll get 1/1, or you'll get 1 hertz. If you put in 2 for t, you'll get 0.5 hertz. If you put in 4 for t, you'll get 0.25 hertz. So a large period corresponds to a small frequency. Okay, good. So here's just a good, nice little word problem here. So Javier is on the swing. His feet brush the ground every 3 seconds. What is his frequency? So to solve this problem, we need to think about how frequency and period are related to each other. If I put in period is 3 seconds, then the frequency should be 1 over 3. But the units now will be 1 over seconds, or hertz, meaning that it's going to be 1/3 of a cycle per second. So, I made a little mistake there. If you think about this here, the brushing the ground every 3 seconds. So draw yourself a little picture, right, of the feet brushing the ground, right? So they're going to brush the ground on the way there, and then brush the ground on the way back. And so that's actually going to mean that it takes 6 seconds to complete a full oscillation. Okay, so a period is how long it takes to complete one full cycle. And so here, if you're thinking about it here, then 1 over 6 seconds, or in other words, this pendulum or the kid on the swing is essentially oscillating back and forth. You could think of it as basically 0.17 of a full cycle per second. So that means that it should take 6 full seconds to complete one oscillation. Okay. So so here's some assessments for us to make sure that we're making sense of things. What is the amplitude, period, and frequency from this graph? Please pause here and take a moment to see if you can figure out what these 3 quantities are. This will definitely be something that I ask you again and again and again throughout the whole term. So please make sure that you are really clear on this point. So take a moment and we'll come back in a second. Okay, we're back. So here we can see that the position of this thing that's moving back and forth is moving back and forth. It looks like from about minus 7.5 up to 7.5 and back, right? And the amount of time that it takes to do that, if I, for example, just looked at the most negative here up to here, it looks like it takes 8 seconds. And another 8 seconds here to get to here. I could also go from 4 to 12, and you'd also see that it's 8 seconds. Or I can go from 6 to 14, it's also 8 seconds. So the period should be 8 seconds. And, the amplitude here, I guess I'll show the solutions to this in a moment, but the amplitude here you can see is 7.5 in the positive or 7.5 in the negative. So we call this as the amplitude is 7.5. To figure out the frequency, that would be in centimeters. To figure out the frequency, then we would just take 1 over the period, so 1 over 8 is approximately, or that's 0.125 hertz. Okay, an object has a frequency of 50 hertz. What's the period? A spring mass system moves from one extreme of its motion to the other once every second. So that means going from, let's say, left to right in 1 second, and then it goes from right to left in 1 second. What is the frequency of this system? So please take a moment to try and answer these questions. Make sure that these are super clear for you. Okay, let's take a look at our solutions. So determining the amplitude, as I mentioned, the amplitude is 7.5 centimeters. You can read these off on the graph here because every increment here on this little rule here is 2.5 apparently, because here's 5, 7.5, 10, so it must be 12.5 and so on. The period is the amount of time that it takes for the oscillation to completely repeat itself. And the frequency, yeah, I don't know, that's pretty weird. I'm not sure why they've, oh yeah, okay, I guess I understand. The reason for this thing is to say basically that that I don't know. I wouldn't really look at it like that honestly, but this is what they're saying is that in 1 second that this oscillation has gone through it's gone through 1/8 of of its cycle. So if you added up 8 of these, 1/8 of a cycle, it would take you through a full oscillation. But the simpler way to think about it is just simply find the period and take 1 over that number, and now you have the frequency in hertz. Okay. So the object has a frequency of 50 hertz now. What is its period? Well, that means that it's oscillating back and forth 50 times per second. So the period must be really tiny. Indeed, if we just take 1 over that frequency, we'll find that the period is 0.02 seconds. Now, I want you to get familiar with writing that in a variety of different ways. So I'm going to actually go back to my notepad here. 0.2 seconds, 0.02, seconds is actually the same thing as 20 milliseconds. All right, equals here, just to make sure it's nice and clear. This is milliseconds, or we would write it as 20 ms. Sometimes we'll even get down to microseconds. That would be 20,000 microseconds, but it's okay for right now. Just to go to milliseconds is enough. And you can remember that there's 1,000 milliseconds is equal to 1 second. And so that's how you can do your multiply by 1 trick to, for example, to convert this number here. I could take 0.02 seconds, and I could multiply. Let's go ahead and add a fraction. We can multiply by 1,000 milliseconds divided by 1 second, and then you can see here that the seconds cancels out, and multiplying by 1,000, I'm going to slide the decimal place over by 3 places, and you'll see that it's 20 milliseconds. So I just want to make sure that that's nice and clear how I get there. You practice it a few times and you'll get better and better at it. Okay, good. So I'm going to go ahead and continue here. The mass spring system moves from one extreme of its motion to the other once every second. So here's another situation, just like I got tripped up for a second with Javier and the swing because I was just sort of going on autopilot for a second, which is it's easy to do. You can see that if you look at really carefully and you draw yourself a little picture, you have this idea that, well, it's going from one side to the other in a second, and then it's going back in a second. So it actually takes 2 seconds to complete its motion. So if the period is 2 seconds, the frequency should be 0.5 hertz, or in other words, 1/2 of a cycle per second. Okay, that concludes our slides for now. Hopefully now you're more clear on our learning objectives, which are to be able to understand period, frequency, and amplitude, to be able to look at a graph and to make some sense of what is the amplitude, what is the period, be able to read that off of a graph. I'd like you to be able to create these graphs as well. Another thing that maybe is helpful to remember is that we were interested in understanding the connection that sound is created from periodic motion. So anyway, these are again our objectives here. Hopefully now you're feeling familiar to convert between frequency and period, or period to frequency. I'm going to give you just a couple more examples here. I think that it's worth it that we just practice it a few times. So for some practice, if I had a sound that was 400 hertz, then that would be my frequency. And I might ask you, what is the period, okay, of oscillation? Okay, that might be exactly a kind of a question that I might ask you on exam. And in order to solve that kind of question here, there's 2 parts. One is that I would just simply take the equation, which let me go ahead and remind us of this equation. This is our equation right here. And I look here and I say, oh, okay, well that's pretty easy. Then it's just T is equal to 1 over F. So that's equals to 1 divided by 400. And if I do my calculation here, I'm going to just bring up a calculator. If I bring up my calculator here, you can see on the bottom I do 1 divided by 400. This tells me it's 2.5 times 10 to the minus 3. This is nice. I use SpeedCrunch because it kind of tells me these numbers. You could also, for example, do 1 divided by 400 in Google, and you see that it's 0.0025, right? So let's go ahead and go with that number. I'm going to just imagine that you're probably using your Google calculator, which is fine for all the homeworks and things like that. I think that's totally appropriate. You might be using your own graphing calculator. So that's 0.0025 seconds. And if you remember how we handled that problem before, we just simply multiplied by 1,000 and we could get it the number in milliseconds. So I could actually multiply this by 1,000, and I can take the decimal over 1, 2, 3, and you can see that this is actually 2.5 milliseconds. So that's the period of oscillations in milliseconds. So I might ask for it in milliseconds, okay? So please be ready for converting between those things, or for trying to find an answer that's going to be in milliseconds. Another example in the audible range is I might say that the period is equal to, let's say, 0.5 milliseconds. And I might ask, what is the frequency of oscillations? Okay, so here I'm going to use that the frequency is 1 over the period. And so here we have to be careful. I said 0.5 milliseconds. So I'm going to do 1 divided by 0.5 milliseconds. So that's 0.5 e minus 3. Or this is 1 divided by, and then I'll just write here seconds as well to remind us. I'm just going to try to be as careful as possible, because I recognize that maybe you're learning right now and you want to know how to do this really perfectly, right? So I'm going to try to be very careful with the units to show you, and then as time goes on, we'll get more and more clear on what we mean when we're doing these things. So here we have 1 over 0.5 milliseconds, or I'll do 0.5 times 10 to the minus 3, and if I can get this correct here, like that, then I can take the reciprocal of 0.5, so that's 1 over a half, which is 2, and then times 1 over 10 to the minus 3. And so if you remember from before, I'm going to go ahead and put my multiplies there, and we have also some seconds as well. So we have 2 times 10 to the minus 3, and then we have 1 over seconds, so inverse seconds, which is hertz. And then we can see from here that this is just 2 times 10 to the third. And then it's going to be inverse seconds, which is hertz. So this means 2,000 hertz is our answer. Okay? So I want you to get very clear on how to do those manipulations. If you need more practice, please let me know, and I'll post more practice on there. You may even find some more resources to help you to convert. But you definitely need to be able to get clear on using these scientific units. So for example, we could also write that this is the same thing as 2 kilohertz. Remember that kilo means times 10 to the 3. So this is our shorthand for being able to write things so that basically, so you don't have to write a bunch of zeros all the time. And so 2 kilohertz is actually like a pretty high frequency. And in fact, maybe one thing I'll do as I close here is I might just say 2 kilohertz tone. And we can, anything that says 2,000 hertz here, we can usually look up a lot of these things online and they'll play it for it. Do you think it's a high pitch or a low pitch? Let's try. So this is a 2,000 hertz or 2 kilohertz sine wave. I recognize it's a little bit annoying, but nonetheless, I think that's it's good to see, to hear what that actually sounds like. All right, so I think that that's all for today. Thank you for listening and for actively taking on the challenges. I hope that the assessments are feeling good for you and that it's making a lot of sense. And I hope that also you are able to connect this with our in-class activities looking at period and frequency. Thank you. Now I have this awkward, I have to find out how to stop there.